In today's video I will be working on node rotations in the cases where grandfather and the children and the grandchild are in the same line. That means the cases, if suppose this is the grandfather, it's the parent, and this is the grandchild, and this should move become like this. Grandchild and child. Similarly, the left and right children will be swapped on the different parent, and for example, and the grandchild's right of parent, and similarly the nodes will move to the between the grandchildren and the grandparent. This is the transformation that is going to happen. So in this cases, the grandparent children, all of them are in the same line. That is, you can see that they are in a straight line. These are the cases, and the another one is going to be where things are going to get reversed. Grandchild, grandfather, children. This is the second case, but it is this same case with all the nodes on different line. So I will name this as left child parent replaces the grandparent. Struct node constant here I will say right child parent, that's the same, and I will also have to add this functions over here. No, I think these transformations are not needed. Because basically it is like right rotations and we have already done that. So let us write insertion. I'm going to keep these functions for now. Maybe it can be useful in the future. So I will say tab So we will be working on insert of red black tree. Let me open Wikipedia for that. So let us start writing code for insertion. Root is there. The insertions are basically the same as the binary tree, but we perform operations after that. So I will say that struct node iterator root sort value. So it is going to be iterator, and I will have to current node is equal to root struct RV node star previous node root So the loop is going to go something like, I will have to say while current node, as long as current node is not null, and as long as the current node is not null, will also have to take care current node is not null. I will have to move left and right. So current node is equal to so current node data is greater than insert value then current node moves to the left, otherwise current node moves to the right. Previous node is equal to current node. Because value already there. Okay, so once the current node becomes null and so I will have to check So I need some functions to generate to deallocate memory. So I will say something like static node star create node int constant value and size of a struct Arduino. Arduino data and color data is equal to value new node color is equal to red new node parent new node left node right is equal to null. Return the new node. After returning the new node, we have our one node red and black node with us. Value is already there, and I will have to say for example, if I say if we are here, that means that current node is null. If previous node else if previous node is there, I will have to say if root is null, that means I will have to return create node insert value. In this case, where previous node is there, it has to be there, otherwise something wrong with the system. So if previous node data is greater than insert value, left is equal to for example, this can be put over here, that struct new node is equal to create node insert value. and new node. And new node. So we have successfully attached the new node to the already existing tree. We have put the parent over here, and the new node color is red. Now we need to organize after insertion. Struct node, sorry, we'll pass the new node. Return the root. This is just a template of insertion. I will be modifying it later. In the organize after insertion part, I'll have to write this function. If RV node is there, Have a nice day after insertion. If red black node is there, then we have to check that if RB node parent has a null parent, and if not RB node parent, then RB node color is equal to black, return from here. This is the one case where the parent is black, and return from there. Where is the insertion? If parent is null, then insert case 1. What is insert case? Make the node color black, and don't do anything after that, and get parent color is equal to black, then insert case 2. Okay, so what it is says, or RB node parent, and RB node has a parent, and RB node parent is black. There is nothing to do in the insert case 2, so basically existence of this case has no significance. If I say nah, it is not okay to write here, so check uncle, get uncle is not null, and get uncle color is red, so it says, will say struct uncle is equal to uncle of a node if uncle and uncle color is equal to red. This is the case that we are looking at. Uncle is there and the color is red. Insert case 3, then so what we have to do, I will say parent of RB node color is equal to BLA black, uncle color is equal to black, grandparent of RB node color is equal to red, and organize tree after insertion. Grandparent of RB node. Parent color black, uncle color black, grandparent color red, and we organize after grandparent, that they need to fix stuff, because there are nodes going to be above grandparent, then they need to be fixed. So next case is else case of case 4, where it is possible that basically I have to say it is saying that one of the parent sibling is either there or it is a black in color. So that is the case 4. What it says it says that if it is parents right on the right child, and grandparents, the parent is the left child, then we rotate to the right, to the left, then in case 2 we rotate to the right. So what it is saying, what it says that if so, thing is, and the issue mainly we are getting over here, that we have two nodes, red nodes attached to each other, and we need to build either we have to add one black node, or we need to put those red colors apart, so that there is no issue between. We need to put some black node between P and N, which is happening over here. Now there is one black node between these two red nodes. So after that, children is already red, this is already red, grandparent is black, so we need to transform in a way that grandparent is moved, becomes the child, and as it is black, we need to turn it into red, and the parent will turn into black. So what we are saying over here, that parent color is going to be black, grandparent color is going to be red. And what it says here, it says we're basically finding the locations, the rotations of these nodes, and it says, I will say, if RV node is equal to parent right and parent is equal to grandparent left, like we have where it is here, children is right and parent is left. In that case, I have written a function for that. Right grandchild replaces the grandparent, so I will use that function. I will say let me explain this to you. If you look exactly what is happening over here, forget about these rotations. So this is the child and they rename the child back to as the parent. So basically the P over here is N. This is the grandchild. It is taking place of this grandparent. So instead of doing these two rotations drama, that we make a left rotation then we make a right rotation, I directly move all the nodes on the proper position. So N becomes the over here, N comes N, where is N? So N comes over here and becomes P. So now parent is equal to this. In next case, RB node is equal to parent left and parent is equal to grandparent right, just the opposite of above. So parent is equal to left grandchild replaces the grandparent and RB node, this becomes the parent. These are the double rotations as per normal coding practice. This will be called double rotations, but I have achieved the same effect in one go. So these are the double rotations that we have, and next is going to be the cases that I said, that where if RB node is equal to parent left and parent is equal to grandparent left, parent is equal to left child, parent replaces the grandparent. So this is the code. Else parent is equal to right child, parent replaces the grandparent, and it is the case, that case. These are more this my code reflects the original intention of the purpose of double rotation, that what is going to happen. Instead of confusing it with multiple rotations, left rotation, right rotation, and just move the nodes on at the correct position. So our code is done, and they are calculating with, that is why I was thinking that they are not, they have void functions, then how they are updating the nodes. So over here they are, what is called, they are calling, they are running another loop to find the root. Okay, and we are doing it without running any loop. Create node creation, static. Node color, maybe I should move this parent over here. Parent of RB node, and I don't need to put return statement over here because this will be called anyway. If parent is not there, then make this colors black. If parent is there and its color is black, then do not enter inside. If we go to this function parent of, where is this parent of, okay, this will get inlined, so there is no issue. If there is no parent, then I will get a null value. So if parent is not null and parent color is black, nothing to do there, because it do here, because this is a valid case. And next, if parent is not there, and if parent is not there, then make this node black. If parent is there, in the other cases, check the uncle. If it is red, then make the parent red, make the uncle red, make the grandparent make the uncle and what is called parent black and grandparent is a red, and restart making what is called organize the tree over again, starting from the grandparent. And next is this. So I think the code is done, and I will return the parent from here. This is because this is the parent of this subtree now. Organize tree after insertion, and this is I think I will have to. We are going to have some issues in finding the root again. I will have to figure it out how to do it. Okay, make other call to find the parent again. No issues with that. Insertion, in this case parent is going to be null. Parent is going to be null, so the node will become black. This is correct. We have to find the parent again, because in cases where the root is not the real parent, then we are going to have issues. Because suppose we are making, suppose in the case is the image. Suppose in this case, where is the case? You will see that the child becomes the parent, and that initial parent is gone. In that case, we will get a wrong value of the parent, and we will have to write a function to traverse to find the parent. But I will find some another way for that. Next is the case of deletion that I will do in some other video. And until then, bye bye, and thank you for watching.